Okay, we'll start the lecture now. In the last lecture, we talked about ABCD parameters. All right, yeah, we say that one very useful way of characterization is the ABCD matrix. Yeah, we can characterize a device in terms of ABCD parameters lah. In other words, once you know the value of A, B, C, and D for a particular device, you don't need to know the circuit inside there anymore. Yeah, you can treat it as a black box. Yet, you can find the voltage and current at the input port and output port for any condition. All right. Yeah. Although during the characterization, yeah, you short or open circuit the port, but when you actually use the device, it doesn't matter whether you connect a 50 ohm or you connect a short or you connect other impedance. All right. Yeah. You can always find the value of voltage and current. Understand? And so it is not a limitation. The shorting and open circuit, yeah, that kind of limitation is only in the characterization process. After that, once you get the ABCD matrix, you can use it for any load condition. All right, yeah, you can even find the overall ABCD matrix. Yeah, when you connect many components in cascade. What you need to do is just multiply the ABCD matrix, yeah, of the first device, yeah, with the ABCD parameter of the second device, and so on. All right, yeah, so this is very useful. For example, if you make a transmitter, you have a signal source, and then you have isolator, you have coupler, you have filter, and so on. All right, yeah. You want to know what is the overall ABCD matrix, right? Yeah, so you can find it, yeah, simply by multiplying the ABCD matrix of the first block with the second block and so on. All right, yeah. This is very interesting compared to other parameters like H parameter, Z parameter, or Y parameter. All right. Even for S parameter, if you want to find the overall effect, yeah, it may not be so straightforward compared to ABCD metrics, yeah, as we will see today. Uh, so we say that you can find the ABCD metric for a series element, yeah, or shunt element. You can find ABCD metrics for a transmission line or any two-port device. We also look at example of ideal transformer. What is the ABCD matrix? All right, yeah. Uh, so today we will look at the application in a while. But before that, let us look at how do we find the overall ABCD matrix using various methods. Of course, the straightforward method is to multiply. You multiply the ABCD matrix of the first block with the ABCD matrix of the second block with the ABCD matrix of the third block. And this is an example for a T network. You can do the same for pi network or any other kind of network. All right. Of course, we have also learned as parameters, yeah, we say S parameter is also very useful for RF circuit design. All right, yeah. In S parameters, we don't look at the signal as voltage and current because the size of the circuit is typically big compared to wavelength. Yeah, it is larger than 1/10 of a wavelength. So it is best to look at the signal as wave lah. So that's why S parameter is very useful lah. Especially if you look at very very high frequency like um, millimeter wave, 5G system, 6G system, then you probably need to use S parameters. Uh, but you don't have to worry. Although you use S parameters, it is possible to find uh, the overall effect of a system consisting of many components connected in cascade. This is what we are going to learn today. All right. Of course, the easiest way, is to convert. After you have done characterization using S parameter method, you can find the value of S11, S22, S33, and so on. Uh, you can convert the S parameter to ABCD parameter. Then you can use the ABCD parameters to find the overall uh, matrix, ABCD matrix. And if you want, you can again convert it back to S parameters. That is one easy way. One easy way to find the overall effect. But you can also do it directly. You can do it directly with S parameters. And this is how to do that. Suppose you have two blocks, A connected to B. Now you want to find the overall effect. You want to find the S matrix of the system instead of S parameter matrix of A and B. As A and SB only relate the wave for the individual block. You have SB and SA. So suppose now you have block A connected to block B. To find the S matrix, the overall S matrix of the system, you need to use this formula. Okay, you take 1 over 1 minus S11 of B multiply with S22 of A. All right, and then the matrix, the value S11, S12, S21, and S22 given by all this formula lah. Okay, here you have delta SA, delta SA. These are called determinant. Determinant. Okay, that means you take the product of the diagonal element S11 times S22 minus away S12 times S21. This is what you learn in matrix. All right, the determinant of the matrix. All right. But this is not so convenient because at any one time you can only work with two blocks. Suppose you have 10 blocks, what do? You need to work on the first two blocks, find the S matrix, and then use this matrix to work with the next block, find the S matrix, and then work with the next block to find the S matrix. Not so convenient, isn't it? All right, compared to ABCD matrix. But there is another way. That is first you do some conversion. But instead of converting to ABCD matrix, you can do a simple conversion, yeah, to a T matrix. Yeah, instead of converting S matrix to ABCD matrix, yeah, you just do a simple conversion. That is, yeah, from S you convert it to T. T is 1 over S21 multiply with this matrix. 1 minus S22, S11, and minus delta X. This delta X is the determinant, the determinant of the S matrix for A and B and so on. All right. So finally, to find the overall T matrix, yeah, like the ABCD matrix, yeah, you just take the T matrix of A multiply with the T matrix of B, and if you have multiple block, you just multiply with T matrix of C and D and E and so on. So finally, you get the overall T matrix. After that, you can easily convert it back to S matrix using this formula. 1 over T11 and so on. Okay, understand? Uh, so this is an easier method to find the overall S matrix. Yeah, compared to the earlier case, yeah, where we need to use this, yeah, which we can only work with two block at any one time. There are other way. Another way is the signal flow graph. You can use signal flow graph to find the overall S matrix. All right. Yeah. So to use signal flow graph, this method is also used in control system, if you remember. Uh, uh, so if you know the S matrix of a block, all right, yeah, you can represent it with a signal flow graph that looks like this. All right, yeah. Uh, S21 is the transmission coefficient, right? Yeah, so you can represent it with a path from A1 to B2. Yeah, because if you take B2 divided by A1, that is the transmitted wave divided by the incident wave. B2 divided by A1, that's the transmission coefficient. Correct? Yeah. And similarly, if you take B1 divided by A2, that is the reverse transmission coefficient. Yeah, so you can represent the transmission from port 2 to port 1, yeah, with a path gain of S12. All right, yeah, from port 1 to port 2 you have S21. Yeah, from port 2 to port 1 you have S12. All right. Of course, when you connect a signal to the input of the device, if there is an impedance mismatch, you get some reflection. Yeah. So reflection will give us B1, isn't it? Yeah. If you input a signal A1, yeah, if there is a reflection, you will get B1 being reflected or coming out of the port. Yeah. So in signal flow graph, you can represent it with a path from A1 to B1. Yeah. And the path gain will be S11 because B1 divided by A1 is the reflection coefficient. All right. Yeah. So therefore, the path gain of this path, yeah, will be S11. Okay. Similarly, yeah, signal transmitted to the load. If you have an impedance mismatch, let's say if jack L is not equals to jack naught, yeah, then you get some reflection. All right. Yeah. So this reflected signal can be represented by rho L. That means if rho L is zero, you have an impedance match, and then you have no signal going back to port 2 lor. Not no signal going into port 2 lor, no A2 lor. Yeah, if row L is 0. Okay, yeah, but assuming row L is not 0, then you have a signal that go back to port 2. That's A2. All right, yeah, and again, if there is an impedance mismatch, similarly, you get some reflection. Yeah, you will have some wave coming out of port 2, which is B2. Yeah, and B2 divided by A2 will be the reflection coefficient of port 2, S22. All right, yeah. So for a two-port network, you can represent it using signal flow graph that looks like this. Yeah, the signal flow graph looks like this. All right, yeah, and then the load, yeah, can be represented by a reflection coefficient. In this case, the second block is a one-port network. Is a one. It has only one port, isn't it? All right, yeah. So it only has S11, which is row L. Row L is basically S11 of the second block, isn't it? And there's no S21 because it's only one port now. Okay, so signal that is reflected back all the way to the source. If there is an impedance mismatch, similarly, some signal will be reflected back to the device. This can be represented by this rho S. Which is the reflection coefficient of the source. Meaning you have a wave going back to the source. If this signal is not absorbed, it is reflected back, and then you get A1. You get A1 not only from the source but also from the reflection due to impedance mismatch, right? But source, the source, is from what we learned, in the tutorial, isn't it? You can find what is the voltage, isn't it? Right? You can find the voltage at this point, and then if you take this voltage divided by square root of the square root of the port impedance, you get A lah. You get A1, isn't it? Whatever voltage that you have, you divide by square root of jack C1. So you can treat the signal going into port 1 from the source, which is the previous block, as BS. So this BS is given by the voltage of the source divided by the total impedance. Total impedance jack S plus jack naught. Jack S plus jack naught. Where jack naught is supposed to be the port impedance of port 1. All right, yeah. But Vs divided by total impedance give you the current, isn't it? So you can also write Bs as current times square root of impedance. Current times square root of impedance. All right. So that gives us Bs. As for rho L is simply the reflection coefficient, right? As we learned earlier, is jack L minus jack naught over jack L plus jack naught. Yeah. And as for rho S, rho S is the same as rho L, except that this time the impedance mismatch is due to ZS, right? And then you have ZS minus Z naught over ZS plus Z naught. So once we have got the value of rho S, rho L, BS, and also the S metric of the device, so now we want to know what is the actual value or measured value of S21. That means now we are actually analyzing the overall S matrix, isn't it? We are considering the case that we have the first block here. The second block is check L. The second block, there is a second block, which we don't assume is an impedance match. So there is a cascade of one block to the next block. Yeah. So what is the overall S matrix? And that is what we want to know. Lah. All right. Yeah. So S21 prime. Yeah. This is the actual transmission coefficient. Yeah. The actual transmission coefficient is B2 over A1. Yeah, it is also B2 over A1, except that this time B2 is not only from the source, but also include any reflection due to impedance mismatch. Eh? So you get the value the given by this formula. And S11 is B1 over A1. Similarly, B1 is not just reflection coefficient, but also some including some signal that is transmitted from port 2 to port 1. Yeah, so you can calculate S11 prime, that is the measured S11 or the actual S11 due to the uh, cascading of two blocks. So the S11 prime will be given by this formula. The question is, how do we get this formula? Do we need to remember this formula? Yeah. What happens if I have 3 blocks, 4 blocks, and so on? How do I get the actual S21 and the actual S11 and so on? Yeah. If I have multiple blocks, how do I do that? So to do that, you can use the method of signal flow graph. Lah. In particular, you can use the Mason's rules. Mason's rules, right? Yeah. You can even include a third block, a fourth block, and so on. You can have another S matrix here. Yet you can find the overall S21 and the overall S11. It is possible. All right. Yeah. So if you apply Mason's rule, first, we need to define what is path gain, PN, path gain. So if you want to find S21, S21 means B2 divided by A1. So you want to find how many ways are there for signal to go from this node A1 to B2? How many ways are there? So you see signal can go from port 1 to port 2. Not only this path, signal can also go all the way, return, and then come back to here. This is another path, isn't it? Yeah. Or signal can also go all the way to the load, come back, get reflected again, and get to B2. Yeah, it's just like you want to go from here to Ipoh. There are so many routes, isn't it? Yeah, not just one route. You can use the straight route. Yeah, you can take the old road, or you can detour to somewhere to buy durian or something. Then only you go to Ipoh. There are many paths, not just one path. Yeah. So each path has a certain gain. It's just like if you take different path, you take different amount of time, different amount of petrol, isn't it? So this that different path will have different gain. The gain is the product of the path gain. For example, the first path is from A1 to B2 directly. So that one is the shortest path. The path gain is S21. P is just S21. Okay, and then there is a second path, right? Yeah, you can go from here to the load and then come back. So this is another path. So the path gain will be S21 times rho L and multiply with S22. All right. Yeah, if you have another path, then you have from here to the load, come back and then go back, to B2. And then in this case, the path gain will be S21 times rho L times S12 times rho S. This is the path gain and the various path. All right, yeah. But that is not all. You must also define what is first order loop, second order loops, and third order loops. Mm. First order loop means the gain of the loop. For example, here you have a loop. There is a loop there. All right, yeah. So each loop has a certain loop gain. This loop, the loop gain will be rho L times S22. All right, yeah. But if you take this loop, this thing, this big loop, all right, the loop gain will be S21 times rho L times S12 times rho S lah. Okay, yeah. So that is called the first order loops. All right, yeah. And then the second order loop is the product of two loop gain. Two loop gain. Let's say you have this loop. One you have one loop gain. Here you have another loop. Another loop. You have another loop gain. The product of these two loop gain is called the second order loops. Similarly, you can have third order loop, fourth order loop, and so on. Okay, third order loop means you take the product of loop gain from three loops, three independent loops. All right, yeah. How do we use the path gain loop and first order loop, second order loop, and so on? We apply these rules. Okay, yeah. The T can be S21, can be S11, can be S12, can be S22, and so on. T can be any path. All right, yeah. So what you need to consider is, you consider how many paths are there. Like what we did just now. How many paths are there to go from A1 to B2? Let's say I call that P1. That is the first path. P A1 from A1 to B2. I have the path gain is S21. All right, yeah. And then after that I need to multiply with something. This bracket is 1 minus the sum of first order loop plus the sum of second order loop minus the sum of third order loop, and so on. Okay, the same goes for the second path, third path, and so on. All right, yeah. But uh, the sum of first order loop here is not all the first order loop. It only include the first order loop that doesn't touch the path. So you have a superscript one here. We are talking about path number one. All right. So if you are talking about path number two, then you have a superscript two lah, and so on lah. All right. So for the first one, you need to find the sum of first order loop gain. First order loop gain. The subscript one means that you only include those loop that doesn't touch the path. And for example, if you take the first path, A from A1 to B2, there is a first order loop here, rho L times S22. But this loop is touching the path. If it is touching the path, it cannot be included. Okay, and then you say, this is another loop. You can call this another first order loop. But again, it is touching the path. It cannot be included in this sum. Similarly, yeah, when you want to take the product of any two loops, yeah, let's say you want to take this loop, the loop gain of this loop, multiply with the loop gain of this loop. Uh, you only take the product of this loop gain, these two loop gain, if both are not touching the path. All right, yeah, here in this case, yeah, these two are touching the path, so you cannot include all this. Okay, yeah, so for this case, you only have one, the rest are all zero. Okay, yeah, you must only choose the loop that doesn't touch the path. All right, yeah, but let's say you take the another path. Yeah, if there is another path, similarly, you will have P2 lah. You have P2, and then you similarly consider only the loop that doesn't touch this second path and so on. Finally, you divide it by 1 minus the sum of first order loop plus the sum of second order loop and so on. At this time, it include all the first order loop, include all the second order loop and so on. It doesn't care which path. Understand? All right. Yeah. Let's say we look at this example. What is the denominator? The denominator is supposed to be 1 minus the sum of first order loop. Yeah. So this is the sum of the first order loop. Okay. Yeah. I have 1 minus. What are the first order loop? I have S11 times rho S. This is one first order loop. And then I have rho L times S22. This is the second first order loop. And then I have this whole thing as a loop. So I have S21 rho L S12 times rho S. This is also uh, the first order loops. Okay, and then I need to add with the sum of second order loop. Yeah, the sum of second order. That means I take the product of any two loop lah. Yeah, any two loop gain. Yeah, here that doesn't touch each other lah. Alright, yeah. So I have this loop and this loop that doesn't touch each other. All right. Yeah. So the sum of second order loop is this one rho L times S22 multiply with rho S times S11. That is this term here. No? Understand? Okay. Whereas for the numerator, what are the path to go from A1 to B2. This is the path. All right. Yeah. We are supposed to multiply with the sum of first order loop, right? Yeah. 1 minus the sum of the first order loop, right? Yeah. But in this case, yeah, we can only take those loop that doesn't touch the path. Yeah. This loop is touching the path. I cannot take this. This loop also touch the path. I cannot take. Yeah, so we are only left with P1 times 1. And P1 is S21. Okay, yeah. So this is how we get the formula for S21 prime. And as for S11 prime, the denominator is the same, but this time we are talking about the path from port 1 to port 1. Yeah, we want to take B1 over A1. Yeah, B1 over A1. So I have one path to go, that is go straight from A1 to B1, from this node to this node, one path. Okay, there is another path to go from A1 to B1. That is, I go from A1 to B2 there, and then through row L to A2 and then to B1. This is a second path. All right, yeah. So for the first path, the path gain is S11. Yeah, for the first path, the path gain is S11. I need to take 1 minus the sum of loop gain. So in this case, the sum of loop gain is only rho L times S22. This is the only loop that doesn't touch the first path. Yeah, so I have 1 minus S22 times rho L. Yeah, the only loop here. Okay, and then I have another part right, yeah, which is S21 times rho L times S12. That is this. So I need to multiply with 1 minus the sum of loop gain, isn't it? Yeah, but there's no loop that doesn't touch this path. Yeah, this particular path, this long path here, there's no loop that doesn't touch this path. So it is just multiply with 1 minus 0. It just multiply with 1 only. That is how we get S11 prime. Okay, understand? Yeah, it may look a bit complicated, but it is possible to write a program to do it. All right, yeah. Uh, okay, any question? This is one example where we use this signal flow graph to to do something useful. All right, yeah. In the use of vector network analyzer in the lab, when you want to measure RF or microwave device, yeah, you can use a vector network analyzer that I showed you earlier, isn't it? Uh, so you connect. If you have a one port network, for example, you have a simple component. Yeah, you want to know what is the impedance, or you have an antenna. You want to find the input impedance of the antenna. That is a one port device. So you only want to know what is the value of S11. Here we put S11A, the actual S11. All right. But in the connection of this load to the network analyzer, you use a cable, isn't it? You have connector, you have cable, and so on, right? Yeah, so in between the load or antenna that you want to measure and the network analyzer, there is actually a device in between. Okay, so whatever that is measured by the network analyzer is the measured value of S11, S11M, is not the actual S11. So we need to know the relationship between S11A and S11M. Then only we can find S11A from the measured S11M. Understand? And the network analyzer give you S11M. But you want to know what is S11A. So this is the relationship between S11M and S11A. How do we get this equation? We represent the cable plus the connector and everything in between, the network analyzer and the load, or the antenna that we are measuring. We represent this whole thing with a S matrix, or in this case, a signal flow graph that looks like this. Okay, so first we need to do a calibration to find the value of ED, ES, and ER. Uh, that process is called vector error correction. All right, yeah, or calibration. Okay, yeah. One method of calibration is called the open shot load through calibration. Okay, for one port device or one port measurement, you only need to do open shot load calibration. But if you have a two port device, you have port 1 and port 2. In this case, you want to measure S11A, S21A, S22A, and S12A. In that case, yeah, you need to do one more calibration, which is the true calibration. All right. Yeah. So what is the meaning of calibration? Yeah. Calibration means the process to find the value of ED, ES, and ER. All right. So how do we do that? We need to measure some known load. We need to measure some known load. Yeah. So the known load that we can measure is open circuit, short circuit, and match load. That's why it's called open short load. Eh? It is a known load because then if you have an open circuit, you know the actual reflection coefficient is 1. If you have a short circuit, yeah, if this device that you connect is a short circuit, you know the actual S11 is minus 1. Yeah, and if you connect a device and that device is a match load, then you know the S11A is 0. Yeah, L will give you S11 is 0. All right. So from these three measurements, yeah, you measure S11M for open circuit. Yeah, when you leave this port of you connect open circuit, you measure S11M, and then you connect short circuit, you measure S11M again, and then you connect match load, you measure S11M again. And you have three value of S11M, yeah, for different loads. Yeah, you solve the equation, and then you can find the value of ED, ER, and ES. All right, yeah, so that is what we call the calibration, vector network analyzer calibration. Okay, yeah, it involves measurement of known load, open, short, and load. So assuming you already know ED, ES, and ER from the calibration process. Now, how do we find S11A? As I said earlier, you need to know the relationship between S11M and S11A lah. Yeah, using signal flow graph. Yeah, from this graph, yeah, what is the path to go from A1 to B1 so that we get S11M. Yeah, so there is one path, yeah, which is ED, yeah, multiplied with 1 minus the loop gain. The loop gain is S11A times ES. Yeah, 1 minus S11A times ES. All right. Then there is a second part, which is uh, from A1 to B2, and then back to A2, back to B1. So the loop gain is 1 times S11A times ER. Yeah, so S11A times ER. That's the second part. Okay. Yeah, you divide by the one the denominator, which is 1 minus the loop gain, 1 minus the loop gain, and the loop, there is only one loop, yeah, which is ES times S11A. All right, yeah, so you get the relationship between S11M and S11A. Uh, so suppose, yeah, you connect the antenna that you want to test, you want to find S11A, you already know ED, ER, and ES. Yeah, from this equation, you can work out. You can work out what is S11A. Correct or not? Okay, any question? All right, yeah. But if it's a two-port network, then it will be more complex. And let's say this is the device that you want to measure, or you want to find the value S11A, S21A, S22A, and S12A. All right, and this is the device that you want to measure. All right. This time, similarly, you need to do calibration, but for two-port calibration, there are 6 parameters, error term. Yeah, this DES, and ER are called the error terms. So one port you have only 3 error terms. For two port you actually have 12 error terms. 4 error terms in the forward path, and 6 error terms in the forward path and 6 error terms in the reverse path. Okay, the 6 error terms are EDF, ESF, ERF. Yeah, here we have three terms. Yeah, like the earlier case. Yeah, we have three terms already. Then we have EXF, ETF, and ELF. Yeah, there are 6 error terms that we need to find. But this is beyond the scope of this course. Just for your information. There are 6 terms. But this is only for one path. From port 1 to port 2. Similarly, if you want to measure the reverse path, from port 2 to port 1, you have another 6 error terms. You have another 6 error terms. All right. Yeah. So in this case, you need to do more measurement of open short load. In particular, you need to do open short load through. That means you need to do open short load measurement at port 1. You also need to do open short load measurement at port 2. And then finally, you connect the cable directly from port 1 to port 2. That is called the through measurement. So with all this measurement, then you can find the 12 error terms. And then from signal flow graph analysis, you can find the relationship between the actual S parameters, and the measured S parameters. You work out, you solve the simultaneous equation, then you can find the actual value of S11, S12, S21, and S22. Understand? Okay. Any question? Okay. Yeah. Uh, I know this is a bit difficult, but do not worry. Uh, I will not ask you this question in the exam. But for your own knowledge, it is good that you try to understand this signal flow graph method. Okay, any question? Okay, any question? All right, yeah, if there's no question, we'll take a break of 5 minutes and then we will continue.